let's look over at Chapter 6, Statistical Concepts, Making Meaning Out of Raw Scores. Let's say that we have Jeremiah and Elise, and Jeremiah scores a 47 on one test, and Elise scores a 95 on a different test. So, who did it better? Well, it depends. What if Jeremiah's score is a 47 out of 52? We'd be like, yeah, he did really well. But what if this is a score on depression? Or what if Elise made a 95, but then we look and it's 95 out of 1,000? The scores are different. So it really depends on if those numbers mean anything. It can look at how many items are there on the test, the average score of everyone who took the test. Is a higher score better than a lower score? So let's take the whole concept of raw scores and break it down in a way that's easy to understand. So let's say that we have a test with several questions. Each time you answer a question, you get a certain number of points. The raw score is simply the total number of points that you earned on the test without any adjustments or conversions. So if a test had 10 questions and you get 8 of them correct, your raw score is an 8. It's a straightforward count of how many points you earned based on your correct answers without considering anything else. Raw scores are like the most basic measurement of a performance on a test. They don't take into account the difficulty of a question or any other factors. It's just a simple tally of the points that you have earned. Thus, we come to rule number 1. Raw scores are meaningless. They tell us little, if anything, about how a person has done on a test. So, what are we going to do with that? If we take those raw scores and we start comparing an individual's responses on their raw scores to a norm group, that's going to give us a little bit more information. So we need to make raw scores meaningful, and we do this through something called norm group comparisons. And these comparisons are helpful because they tell us the relative position within the norm group of a person's score. So let's go back and say that Jeremiah and Elise had taken the same test. We can now look at them and see how those scores are alike and are they different. Because let's say we're testing them, they're the same age or in the same grade. We're going to be looking at reading comprehension. Now we can look at those two scores and say, hey, one scored higher or one scored lower because we have the different variables that go into the test. But the second one is they let us compare the results among test takers who took the same test. Let's say that we had a parent and they had a pair of twins who were in the 3rd grade, and we gave both of these children a reading test. We could look at those scores, the raw data, to see which one scored higher, if they both scored higher, or if there was one who was struggling. And they also allow us to compare test results on 2 or more different tests that are taken by the same individual. So if we had a kid who took an achievement test and then a child that took an aptitude test, and we're like, hey, there's a large discrepancy between these two, it could indicate a learning disability. And so when you hear as a school counselor that the school psychometrist or the school psychologist has come in and has given some of these tests to a student, that's one of the things that they use to see if a student might be in special ed or if they may need additional assistance to be successful in school. All right, mathematics concept. Okay, frequency distributions. Frequency distributions are great because they help us make sense of scores. And a frequency distribution, all it does is order a set of scores from high to low and list the corresponding frequency of each score. Let's take a look at it. So over here we have a score column, and then we have F, which is our frequency. So the score column is where we write down all the possible scores, like 66, 63, 60, how we have those going down there. And the frequency column, here we write down how many students got each score. So for example, if 3 students got a score of a 57, you would write a 3 in the frequency column. This table helps you see at a glance how many students got each score, so you can add more scores and frequencies as you need. And it's a handy way to organize information about test results. So why is this helpful for us? A frequency distribution table is helpful because it provides a clear and organized way to understand the distribution of scores in a data set. So let's take a look at some of those. How is that helping you as a school counselor out? Well, one, there's a quick overview. You can quickly see which scores are more common and which are less common. So this gives you a snapshot of the overall performance of the group. It also helps you identify trends. So patterns in the data become more apparent. For let's say that you might notice that a lot of students scored around 78, which can indicate a particular difficulty level or a topic that needs more attention. Shows a central tendency. It helps in understanding the central tendency of the data. For instance, you can easily identify the mode, which is the most frequently occurring score, by looking at the frequency column. It also allows for easy comparison between different groups or data sets. You can create separate frequency distribution tables for different classes or different time periods to compare them to identify trends or differences. So let's say that you were teaching a class about some type of social skill. At the beginning of and we'll talk about this more as we go along in the school thing, but at the beginning of each lesson, you're supposed to give them a short evaluation to see where they are. So you could ask them a few questions on a Likert score, like on a scale of 1 to 5, how much do you know about this topic? And then at the end, you could use it again and ask them how much they know. So hopefully we're going to see that from the beginning to the end, they have learned something. But let's say that you look at the pretest, the Likert scale that you've done at the beginning for maybe your third period class and then your fourth period class. And you see that those in the third period class had way low scores. Like none of them knew anything about what you were going to talk about. But then the fourth grade class or the fourth period class, they did know a whole lot about it. So that right there helps you kind of have a frequency distribution. You're able to see some trends in the differences. It's also great for interpreting data. If the scores are spread out over a wide range, it suggests that there's a variability. But if the scores are clustered around a specific range, it indicates consistency. So in an educational setting, teachers might use frequency distribution to decide where to focus additional teaching or resources based on the areas where the students seem to struggle most. So you would know, like in the one that I was talking about, that the kids in the third period class, they may be struggling or they may be doing better than the fourth period class. It just depends when you kind of compare that data. So in summary, a frequency distribution table simplifies complex data, maybe making it easier for us to analyze and draw meaningful conclusions. It's a foundational step in statistical analysis and helps in making informed decisions. Let's make our own frequency distribution table from some numbers. So here I have a chart of random numbers that I have made for you. They're just all kinds of numbers there. So let's take the numbers and figure out how they go. I'm going to count how many times the numbers are in here. So I see the number 1 and I'm counting it 1, 2, 3, 4, 5, 6. So that number 1, I'm seeing it 6 times. And I won't go through all of them with you, but I've counted them again. Number 2 is 2 times. Number 3 is 6 times, and it kind of goes on and on like that. So the count for each number in the set, I have 1 6 times, 2 2 times, blah, 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 8 5 times, and 9 2 times. So to make a table out of that, it's really, really simple. You're just putting the number and the frequency that you see it. So you're seeing 1, and you're seeing it a frequency of 6 times. So the frequency is showing how many times each unique number shows up in the individual set. All right, so now that we have our some of our raw data, we're going to want to take that and make it into something a little bit more easy for us to read. And the way we do that is by using 2 different types of graphs. One of those is known as the histogram or the bar graph, and the other one is a frequency polygon. That sounds like a lot of fun. So let's see how that works. Before we're able to make either one of those, we have to determine what our class intervals are. I'm going to try to explain it in 2 different ways for you. This is super, super basic. So let's imagine that we have a big jar of candies, or just some candy, and I dump it out all on the desk, and we've just got a ton of candy. And I want to organize it. So I say, let's take all of the candies and take each individual color and group them into color ranges to make it simpler. So first of all, let's define the color interval. So I'm going to say I want to have red, and I want to have green, and I want to have yellow, and then it looks like I also have some oranges and some nuts and some raisin. So I'm going to have those go all across. So I will sort my different candies into the intervals. So all the candies that are red are going to go over into my red section. Those that are green are going to go over into my green section, and so on. So I can count the candies that are in each interval. So after I sort them, I'm going to count them. And that way I can get an overview of the distributions of colors that I have on my table. So let's think about it a little differently. Instead of dealing with candy, now we have a simpler way of understanding the overall mix of colors and how many different colors that I have. Let's look at it in terms of a class. So imagine that you're a teacher and your students have just taken a math test. You want to understand how well the class performed on the test. So instead of looking at each individual score, you decide to use class intervals to help simplify the analysis. So you decide to group the test scores into intervals. For example, one is going to be 0 to 50, one's going to be 51 to 60, 61 to 70, 71 to 80, and 81 to 100. And I can sort those into the different scores. So from 0 to 50, I only have one student that's in that group. If I'm going up to 51 to 60, I have 1, 2, 3, 4, 5, 6 kids in that group. 61 to 70, I have 2, 71 to 80, I have 3, and 81 to 100, I have 5 students there. So being able to look at these intervals like that, it helps me get a better idea of how the scores are going. So this is going to help me because I'm going to be able to see certain score ranges where my students are performing well or where they are struggling. So they're doing great in these right here, struggling right there. So it's a simplified way of understanding the overall performance without getting lost in individual scores. So if we go back into our textbook on page 113, we have, not 113, this is on 112, we have that original frequency distribution that we were looking at. Distribution, the scores, and how many times that we are seeing them. All right, so let's move on over into here a little bit more. Now I'm going to move those into intervals, into class intervals. So I'm going to break the intervals down into different groups. So I'm going to do it in an interval of 5. So here's 62 to 66, 57 to 61, and so on. How do I know there are 5 intervals? It's going to be like for 32 to 36, I've got 32, 33, 34, 35, 36. So it's an interval of 5. If we look at this, we're going to see there were 2 students who were in the 32 to 36 range. Don't let me confuse you, but I'm going to go back to this original table that we have. And students that go 32, 33, 34, 35, I can count that, and there are 2 students that did that. And looking over here on my other interval and frequency, I've got 2 students, those 2 students that were in that range. So having the intervals is going to be very easy for me because now I can make a histogram with those intervals that are based on the range of 5. So here are my class intervals, 32 to 36, 37 to 41, and so on. And here we go. I have 2 people that are in that range. As we go up, it comes up to 5. Up here we have 10. My highest one is a little bit between 25 and 30, and then it goes down again. So this histogram is a graphical representation of the distribution data. So I can see the intervals and I can see the frequencies on the histogram. The horizontal axis represents the class intervals, and the vertical axis represents the frequencies. All right, so we have a histogram, but let's go over and look at a frequency polygon. Instead of it being a bar graph, now we're looking at it more as a line graph. You guys can probably understand this really well. So instead of the bars, I just have, again, the class intervals and the frequencies, and I've just plotted that by the different points, and I have drawn a line on it. So that is a frequency polygon for the intervals that have a range of 5. And again, we're basing that on our table that we had earlier in the chapter. Let's look at a cumulative distribution. And cumulative distribution helps us because now we are moving on from just having this raw data in the histogram or in the little in the frequency polygon that we have. This is better and it's more helpful to convey information about the percentile rank. And we will look at percentile ranks a lot as school counselors when we're looking at data because that helps us see what students are falling through the gaps, what do we need to focus on and able to close the gaps and to help them to be successful as our students. So we're going to look here on page 115. We have table 6.3, which is a percentages calculated for a cumulative distribution. Let me fix my notes. Okay, so let's say that we have a group of students and they take a test, and this is a summary of their scores, but we're going to end up doing it in a way that's easier for us to look at. So as we talked about before, the class intervals, we did those in bits of 5, so 62, 63, 64, 65, 66, so intervals of 7. And the frequency is the number of students who scored in that class interval range. And the percentage here is saying, out of all the students, what percentage got scores in this range? So for the first one, between 62 and 66, it is 3% of all the students. And you'll be like, well, how did you end up getting that? Let me show you over here. Okay, to find a percentage for a class interval, you're going to divide the frequency of that interval by the total number of observations and then multiply for 100. So for this first interval right here, for the 62 to 66, we are going to take the frequency, 2, divided by the total, and the total is the total number of students who we are observing, and in this case it is 62%. So it's 2 divided by 62 times 100, which roughly comes out to be about 3.23%, and for this table we're just going to round it down to 3%. Alright, so let me go back one more here with my notes. Okay, so then how did we get the cumulative percentage? Okay, the cumulative percentage is adding all the percentages as you go up the table. So it tells you the total percentage of students who got scores at or below a certain level. So let's look down here at the bottom. Between 32 to 36, we had 2 students. And like I showed you before, that ends up being about 3%. So our cumulative percentage there is 3. So now we're going to move on up. In the 37 to 41 range, we had 5 students, which ended up being a percentage of 8. So we add them. We add the 3% here from the cumulative percentage to the 8, which equals a cumulative percentage of 11. And as we keep moving up here, we have 16%, so we add the 11 to the 16, and it's 27. And as we keep adding them up, we come up with a cumulative percentage, which is always going to be 100. So that's saying that all of our students scored between 66 all the way down to 32%. Let's look at that on a graph. Okay, here we are. We have our cumulative percentage over on the y-axis. On the x-axis, we have our class intervals, and we have plotted those on this, and we see a nice little curve there. Well, let's say that we hear from whoever the people that tell us what the cutoff is. If they came in and said, okay, for a statewide proficiency exam, the cutoff score for our kids is 42%. So I have added just a little red line there just to show us at 42%. And if we look at these kids down under here, we've got about 19% who did not pass. And that helps us understand, ooh, these kids are having some problems. We need to see what are they missing and what kind of things can we do to help them be more successful in this particular area. Okay, let's move over into normal curves and skewed curves. So let's imagine that we have a class of students and we are looking at their test scores. The normal curve is a special shape that often appears when you graph how many students get different scores. So here's how it works. Most scores are in the middle. Picture most students getting scores somewhere right in here. So we're saying, hey, a lot of students did okay on the test. But we're going to have some at the extremes. So imagine fewer students getting really high scores or really lower scores. Not every student aced the test and not every student did poorly. So if we'll see this a whole lot. And if you graph a lot of these scores, you get a special curve that's like a hill in the middle. It's higher in the middle and lower on the sides. And this curve is called a normal curve because it's a very common pattern. It is bell-shaped. People call it a bell curve because, well, it looks a bit like a bell. The top is in the middle and it slopes down on both sides. And this is great for us when we're talking about statistics and doing prediction. The curve is handy because in many situations it helps predict where most things or most people are. For example, if you know most students score around a certain point, you can guess that new students might also score around there. So the normal curve is like a friendly shape that shows up a lot when we're dealing with groups of things, and it helps us understand where most of those things are likely to be. So here's an example right here of how a normal curve usually works. And this is what we'll see most of the time when we're looking at test scores, that the majority of people will fit right in the middle, and you're going to have some outliers on both the positive and negative side. So that runs us into rule number 2. God does not play with the universe, said Einstein. Raleigh. So perfect are the laws of nature that some see this as the creation of a perfect God who has set the motion of the wheels of the universe, who has set in motion the wheels of the universe. So whether or not you believe this is a God-inspired phenomenon, it has great implications for testing. Concepts such as the bell-shaped curve are crucial to our understanding of norm reference tests and allow us to compare individuals. The difference between normal and skewed curves. So we had the normal curve that we were just talking about and what it looks like there. But if we go on, we have a negatively skewed curves, and it kind of looks like a backward slide. But what happens in a negatively skewed curve is most of the scores are on the higher side. Yay, things are going well. But then there's some that are on the lower side. So it would be me saying, hey, a bunch of students did really well on this, but a few struggled on the negatively skewed. So on the positively skewed curve, most of the scores are on the lower side, but some of the scores are on the exceptional side. So it's like saying, most students they kind of did okay, but there are a few students who really, really knocked that out of the park. And you're going to see this on different types of testing data that you'll see in the future. And this moves on into measures of central tendencies. And this helps us put meaning to scores. It tells us something about the center of a series of scores and focuses on the mean, median, and the mode. So let's have a little bit of fun checking those out. So all right, let's imagine that we're talking about your favorite toy collection, and we want to figure out where most of your favorite toys are placed. Measures of central tendency help us understand where the center of our collection is. So the mean of average toys. Think about the mean as the average. If you had 10 toys and you'd add up the number of toys and then divide by 10. For example, if you have 3 action figures, 5 stuffed animals, and 2 cars, you'd add them up. 3 plus 5 plus 2 equals 10. And then divide by the 3 types of toys, giving you about an average of 3.33 toys per type. Oh, and here's the little thing for it right there, is M is the sum of everything divided by the total number of things. And here we have the median. Now this is kind of in the middle. Picture that we took all your toys and lined them up from the one you like the least to the one you like the most. The median is in the toy that's right in the middle. So if you have 5 types of toys, the one that is right there in the median is the middle. But let's say that you have an even number, like 6 types. What you do is you take the average of the 2 toys in the middle, and that would give you the median. Next up is the mode, and the mode tells you what the most popular toy that you have is. So for example, in this thing, we have 5 robots, we have 2 stuffed animals, and 4 cars. So that would mean that the robots there would be the mode because you have the most of them. So let me do this in and explain to me like it's 5 little summary. The mean is the average. If you want to know how many toys you have on average, you add them up and divide by how many there are. To get the median, imagine that all your toys are lined up. The one right in the middle is the median or the middle toy. And then the mode. The mode is the toy that you have the most of, and it's the one in your collection that shows up most frequently. Example that it's coming from the textbook on page 118, and it just kind of shows you a little bit about them determining the measures of central tendency, which is what we've been talking about. So here we have the mean, and that's when we take all of those and sum it up, and there we go. We sum it up and divide by how many numbers we have. We have the median, which is the middle number, and if you look on here, we've got 5 going up and 5 going down, so the one that is in the middle. And then finally the mode, and that is the one that we have that we have the most numbers on. All right. When you are looking at measures of central tendency, you're going to see a negatively skewed curve, a positively skewed curve, or just a normal curve that looks like this. And in a normal curve, everything is lined up. The mean, median, the mode are all together. But let's say that we have say that we have a positively skewed curve. So what does that mean in terms of measures of central tendency? Say that you had this English test and it was worth 100 points. And most of your friends, they did pretty good. They're kind of right in here around 70 and 80%. They understood the materials. And then there were a few superstars, because you know there's always superstars who did really well, and they're over here because they absolutely aced the test, getting scores like 95 or even 100. So if we picture the scores on a graph, it's like a hill that's leaning towards the right. Most of the scores are over on the left side, but then there's a tail right here of the few super high scores. So this is what it is in terms of numbers. The average score, which is our mean right here, it's a little bit higher because it was influenced by those super high scores by the super nerd kids. So the middle score, the median, which is right here, that's going to be more typical. And the most common score, the mode, is going to be closer to what most people got. So in a positively skewed English test, most people did well, yay! But then there were some superstars which ended up pulling up the mean on those scores. So let's take a look at a negatively skewed curve. Let's look at it again from the point of the English test. So you took this challenging English class and it was a pretty hard test. And most of your friends, they were struggling a bit. So right in here, they came in with scores about 30 to 40 points because it wasn't an easy test and they really struggled. But there were some students who really did a bad job, okay? And we can see that tail of those scores coming down. So their scores are a whole lot lower, like 10 or 15 points lower than what everybody else got. So if we're looking at this on a curve, it's a graph. It's like a hill that is leaning over to the left. Most scores are over on the right side, but then there's a tail of a few scores that are very low on the left. So in terms of numbers, what does this mean? So the average score, which is the mean, might be lower than what most people got because it's influenced by the regular scores, but then also those scores that were really low on the other side. The middle score, or the median, that would kind of be the most typical score that most people got. And the mode, hang on, let me think. Yeah, the median, the middle score is going to be more typical, and the most common score is actually going to be the mode right there. So in a negatively skewed English test, most people found it pretty challenging and they struggled, but there were a lot of those that didn't do quite so well, and that pulled down the rest of the curve. The last part of this chapter deals with measures of variability. Things that we're going to look at are the range, the interquartile range, and the standard deviation. So first off, we'll start with the range. Picture the test scores of all the students in your schools lined up. Some students may have high scores, while others have lower scores. The range is like looking at the lowest test score and the highest test score. If the lowest score is 50 and the highest is 90, the range is 40 because it's the difference between the highest and the lowest scores. This here looks at spread in the middle. Imagine that you're a school counselor looking at everyone's emotional well-being scores. The interquartile range is like checking how much the emotional scores vary in the middle, where most of the students are. If the spread is small, it means the middle emotional scores are close. If it's big, the middle emotional scores are spread out. So the interquartile range helps the school counselor focus on the emotional well-being variation within the middle half of students, providing insights into the diversity of emotional experiences without being heavily influenced by the extremes of the high or low scores. Imagine that your school counselor is looking at everyone's emotional well-being scores. The interquartile range is like checking how much the emotional scores vary in the middle, where most of the students are, even if the curve is a bit lopsided. If the spread is small, it means the middle emotional scores are close, even in a skewed curve. If it's big, it means the middle emotional scores are more spread out, adapting to the shape of the curve. So, the interquartile range in a skewed curve helps the school counselor focus on the emotional well-being variation within the central portion of students, considering the unique shape of the distribution. Here we have, finally, the standard deviation, and this describes how the scores deviate from the mean. Here is an Explain It Like I'm 5 summary. Imagine your classmates' heights forming a bell-shaped curve. Standard deviation is like checking if everyone's height is close to the middle, the small standard deviation, or if some are much taller or shorter, which would give a big standard deviation. So standard deviation, when linked with the normal curve, helps us understand how much the values in a set, like heights or test scores, vary from the average. A small standard deviation means values are close to the average in a tight bell curve, and a larger standard deviation means the values are more spread out in a wider bell curve.